let's get started. So talk about some exponential growth and decay for a second. Here's an example of a question you might see. Cesium has a half-life of 30 years. Suppose we have a 200 milligram sample. How much mass remains after T years? So this is kind of a question that you might see. And really all this says is set up the model for exponential decay here. So you're going to start with the usual y equals c e to the kt, or however you like to write it. And then your job is to use the given information to find c and k. And I typically prefer to write this down as a table, as you've seen me do many times. Of course I can. So we know that we're starting with a 200 gram sample. So at times 0, we have 200 grams. And then we are given another data point. It's just kind of hidden. We're told that cesium has a half-life of 30 years. That means that 30 years later, we should have 100 grams. In fact, every 30-year time period is going to multiply by the same fraction, right? I was kind of saying that last week, I think, about how with exponential growth and decay, it's your set time period is the same multiplicative factor of however much stuff you have. So another 30 years, we get us to 50, another 30 years, we get us to 25, and so on and so on and so on. We don't need that data, but it's just useful to think about what's going on here. So let's find, why don't you all find C and K? So plug in this data point, find C, plug in that data point, find K. And you can't see anything because something's happened to my, so I wrote things there that you can't see. Luckily, you don't need them. I'm going to fix this while you work on that. What's going on here? There we go. Sorry, I did, yeah, okay, there we go. Now you can see the things I wrote. So go ahead, find C, find K, find your model. So typically, if you're given the amount of stuff you have times 0, it's easy to find what your C value is. That's just going to be that amount. So our C was just 200 here. And then we use that number, plug it into the model. And then after that, we plug in our other data point to find K. So if I plug in 100 for Y, 30 for T, and also use my C value of 200, then I can solve for K. Dividing both sides by 200, I get 1/2 equal to e to the 30K. Take the natural log of both sides. Natural log of 1/2 equals 30 times K. So in this case, the natural log of 1/2 divided by 30 is equal to K. And if I stop there, I haven't quite answered the question. Because the question says, how much mass remains after t years? So they actually want us to write y as a function of t. So what we should really do is write that y equals 200 e to the natural log of 1/2 over 30 times t. That is the answer that they're looking for when you ask that kind of question. So whatever the way I would phrase it, I would just phrase it as find a model for the amount of mass at time t. But this is how often the question gets phrased. After you've done, in fact, I wouldn't even ask this question personally. I would just be like, how much? I would ask the next question. I would say, find how much of the sample remains after 100 years. So you have to do all this work before you can answer the next question. But then we can ask those questions like, great. How much mass after 100 years? This is also, by the way, why I like to write down a few more numbers over here in my table, because I wrote down every 30 years it's going to be decreasing by half. So I know that after 90 years there should be 25 grams, and after another 30 years there should be like 12.5. So somewhere between 25 and 12.5 grams is how much I should have after 100 years. But we can just answer the question by plugging in 100 to our model, which we can't quite see. Sorry about that. So you just plug in t equal to 100. We're going to get y equal to 200 e to the natural log of 1/2 over 30 times 100. These ones always kind of feel pretty unsatisfying because there's not much more you can do there other than get out your calculator and find out the answers. If we get out a calculator, I guess we can do it. Let's see here. So we've got, let's write, just skip the 200. We've got e to the natural log of 1/2. I feel like I'm going to mess this up with my calculator. Let's just grab some more parentheses here. Parentheses, natural log of 0.5 times 100 over 30, or 10 over 3. And then multiply that by 200. 19.8. So as expected, right? I knew I should be getting somewhere between 25 and 12.5. So I see the answer. I'm like, okay, I didn't screw it up. I know I did the right thing on my calculator. But it's good to think about what your answer should be. So that if you do get an erroneous result here, you can be like, oh, I need to go back and check my work. So we're getting about 19.8 grams. Cool. The other type of question we often ask is, instead of how long until we get the symbol, or is it how much will we have after so many years, we ask how long until we get such and such an amount. So these are the very kind of standard exponential growth and decay questions. The other one here, let's see, right, how long until only 5 grams remain? So this is the other version where instead of setting time equal to something, you're going to set the amount equal to something and solve for time. So we're just going to set 5 equal to 200 e to the natural log of 1/2 over 30 times t, and then solve for t, much like we solved for k. So divide both sides by 200. You get 5 over 200, which should reduce, equal to e to the natural log of 1/2 over 30 times t. Take the natural log of both sides, so we get the natural log of 5 over 200 reduces to 1/40th, or you could write it as a decimal, 0.025, equals the natural log of e to all this is just the all that, so the natural log of 1/2 divided by 30 times t. So we multiply both sides by 30, divide both sides by natural log of 1/2, and there's your very unuseful answer if you don't use a calculator. Because again, I have no idea how long that really might be, right? I know that, so just looking at how much time it should take, looking back at this for a second, I know that after another 30 years, I'm getting down to 12.5, and after another 30 years, after 150 years, I'm getting down to half of 12.5, which is 6.25. So it should be more than 150 years. Let's check. If we do this, we get the natural log of 1/40th divided by the natural log of 1/2. And then multiply that by 30. Yep, looking good. 159.6 years. Let's round it up to 160 years. Yeah. Reduce 5 over 200. So I just divide that. So right, 5 divided by 5 is 1, 200 divided by 5 is 40. Let's look at one more example in this genre, meaning let's look at a Newton's law of cooling example, which are really, it's really just another example of exponential growth decay. It's a little bit more complicated. So let's look at this following question. So we have a cold drink is taken from the refrigerator. You drink it immediately because you want it to be cold. Cold drink is taken from the fridge. And what do we have here? The temperature is 5 degrees Celsius after 25 minutes in a 20 degrees Celsius room. Its temperature is 10 degrees Celsius. So the two questions we're going to ask are, what's the temperature after 50 minutes? 50 total minutes from when we removed it. And that's actually something I should point out. Whenever you're asking these kind of questions and they say like how long or what's the value after so much time, they always mean how much time from the original moment of observation when you did the thing, not 50 minutes after the 25 minutes already passed, unless they specifically said otherwise. You should always read that amount of time as amount of time from the beginning of the process. And then the second question we're going to ask is going to be, when will the temperature get to 15 degrees Celsius? And before we can do any of this, we have to figure out what the model for the temperature at time t is. I never remember this stupid equation. I've seen this equation so many times in my life. I could probably figure it out if I really had to. But honestly, the equation I'm going to remember is that the thing that kind of defines Newton's law of cooling, which is that the rate of change of the temperature of the object with respect to time is proportional to the temperature of the object and the temperature of the surrounding environment. That is where I always start. I don't know how to do it any differently. Now I know what this leads me to. I know that this leads me to saying that the difference in the temperature and the surrounding object, surrounding room, whatever, environment, is equal to CE to the KT. Just like the differential equation we've been dealing with, that dy dt equals a constant times y, or the rate of growth of the population is proportional to the population size, leads to exponential growth. Y equals CE to the KT. It's essentially the same idea, except we're using T minus the surrounding temperature instead of Y. But it's the same deal. Your book even does it that way. Like when they solve this differential equation, they just replace T minus DS with Y and then do the whole same thing. Okay, so now we have to plug in, really we have to read the question to figure out what's what, which is kind of always the case for these problems. So reading this question, we know that the cold drink is taken from the fridge, temperature is 5 degrees. So I'm going to make my little table that I usually like to make. So I know that at time 0, the temperature of my beverage is 5 degrees. And then 25 minutes later, the temperature of my beverage is 10 degrees. And then I know that the surrounding room is balmy 20 degrees Celsius. So that's my TS. So we know that the temperature at time t is equal to 20 degrees plus CE to the KT. You can memorize more than this, right? You can memorize that the C here is, I couldn't even tell you. I know it's the difference between the temperature of the object at the beginning and the surrounding temperature, but honestly, I'm not trying to take up that space in my brain, right? I'm trying to just use the things I have to figure it out on the way. So let's plug in our points here and figure out what's what. So if I plug in time equal to 0 and temperature equal to 5 degrees, I'm going to get 5 for the temperature equals 20 plus CE to the K times 0. Great, so C is going to equal negative 15. Cool. And then we do the usual thing, right? These exponential growth decay problems are always the same stuff. You plug in the first data point to find the first thing, you plug in the second data point to find the second constant, and then after you found the constants, then you answer whatever questions are being asked. It's really, really very much the same process every time. So then we're going to plug in 25 for the time and 10 for the temperature. So we're going to get 10 for the temperature equal to 20 plus -15. Let's just write -15 times e to the k times 25 minutes. And now we're going to solve for k. Be careful here. You have to make sure you do the order of operations correctly. We're going to subtract 20, then divide by -15. So we're going to have 10 minus 20, so -10 equal to -15 e to the 25k. Divide both sides by -15, so you get positive 10 over 15 equals e to the 25k. Take the natural log of both sides. The natural log, 10/15 reduces to 2/3. So the natural log of 2/3 equals 25k. And then finally, the natural log of 2/3 divided by 25 is going to equal k. Great. Now we have all the pieces we need to figure out what the model for the temperature at any time t is. So our model now, we're just taking this general model and plugging in our particular constants. I think we can fit it right here. So our temperature at time t is going to be 20 minus 15 e to the natural log of 2/3 over 25 t. That's the temperature at any time. And now we can answer the questions that we've been asked. What's the temperature after 50 minutes, and when will it be 15 degrees? Ooh, the 50 minutes one I think is actually kind of nice because we can do something kind of fun. Yes, I said fun. So write this down again, just so we have it right here. All right, so if we plug in 50 minutes, we have the temperature at time 50 is going to be 20 minus 15 e to the natural log of 2/3 over 25 times 50. So when the amount of time is an integer multiple of how long it took for the thing to happen in the first place, right? In this problem, it took 25 elapsed minutes for the temperature to do a thing. When that's the case, when you're given an amount that's double that or triple that or some integer multiple of that, you can figure the rest of this out mostly without a calculator. Here's what I mean. This part right here, we can write this as 20 minus 15, and 50 over 25 is 2. So we have e to the 2 times natural log of 2/3. We can rewrite that as e to the natural log of 2/3 squared. I have too many parentheses, that's all right. And then e to the natural log of 2/3 squared is just 2/3 squared. So we can simplify this in a very convenient way. It's going to be 20 minus 15 times 2/3 squared. That's just going to be 20 minus 15 times 4 over 9. Cancel a 3 here, and a 3 here. So you have 20 minus 20/3, which is going to be 60/3 minus 20/3, which is 40/3. And if you do 40 divided by 3, that's 13.333 forever. So the temperature after 50 minutes is 13.3 approximately degrees Celsius. Cool. What else does that tell me? Well, the next question is asking how long until you get to 15 degrees. Now, this one's kind of interesting. Is it going to take longer than 50 minutes or less than 50 minutes? Well, let me ask you, is the soda can getting colder or warmer? Getting warmer, right? It came out cold, it's in a room that's warmer than it, so it should be getting closer to the temperature of its surrounding environment. So we haven't quite finished our journey to 15 degrees, right? We've gotten up from 5 degrees to 13 degrees, but it's going to take a little bit more time to get to 15 degrees. Probably close to an hour. I'm really just guessing though. So the math here is, again, the same as the math we've been doing for all these other problems. We're going to set our temperature at time t equal to the desired amount of 15 degrees. And then we're going to solve as we typically would. So let's see. So taking this equation, solving for t, we do the usual things. We subtract 20, we have negative 15 e to the stuff equal to 50 minus 20 is negative 5. Divide both sides by negative 15. We get e to the natural log of 2/3 divided by 25 times t equals 1/3, because 5 over 15 is 1/3. Take the natural log of both sides. You get the natural log of 2/3 divided by 25 times t equals the natural log of 1/3. Finally, solve for t. You get t equal to 25 times the natural log of 1/3 divided by the natural log of 2/3. I will point out, it's totally okay to write the natural log of 1/3 divided by all this. I just think it's terrible. I don't like having fractions and fractions. So I always like to think of multiplying both sides by 25 and dividing both sides by natural log of 2/3 instead of dividing the whole thing by natural log of 2/3 divided by 25. But again, that's just my preference. It's really fine to do whatever. All right, let's see what we got, just because I want to know. 25 times the natural log of 1/3 divided by the natural log of 2/3. It's interesting on this calculator that does division like that and not as like a little like slash. 67. Yeah, that seems okay. Yeah, sure. Approximately 67.7 minutes. That's right. Longer than 50 minutes, as we already said, should be the case. All right. Let's do one more thing here because someone asked, I think it's worth exploring. Someone asked about like how E was defined to be this limit thing that we've kind of talked about. That maybe you've talked about. I mean, I imagine Adele has talked about it in class a little bit, how E is equal to the limit as n goes to infinity of 1 plus 1 over n to the n. Equivalently, you could also say E is equal to the limit as h approaches 0 of 1 plus h to the 1 over h. And apologies that my n's and my h's do not look that different. The same thing, just different. I know it's kind of terrible, but sometimes it's more useful to look at it this way. Sometimes it's more useful to look at it this way. But the way I would want you to see this, especially when you start talking about L'Hopital's rule in section like 4.3, is that you essentially have something that's very, very close to 1 raised to a larger and larger and larger power. So here, right, 1 over n is getting very, very small. So 1 plus 1 over n is really, really close to 1. And this power is getting very, very large. So here you have something close to 1, power is very big. Same deal over here. If h is going to 0, then this inside part here is close to 1, and this power, 1 divided by something that's getting very small, is going to get very, very big. So people often refer to this as, I guess is the word I'm looking for. Sorry. In this case, well, so if you divide by a really small number, like 1 divided by 0.000001, that's going to be really, really big. And I'm kind of ignoring whether it's coming in from the negative or the positive side. It ends up not mattering, but it can be kind of hard to see from the other side. Oh my gosh, there's the word. When we have a limit that's a 0 over 0, it's a, yes, indeterminate form. Good God, why couldn't I think of it? Okay, so this is another type of indeterminate form when you have a limit. So we typically call this a 1 to the infinity indeterminate type. Now, what I really want to make sure that you understand with this is that 1 to the infinity is not 1. Because you don't really have 1 to the infinity, you have something that's really, really close to 1, but a little bit bigger than 1. And when you take a number, well, in fact, let's actually look here. So here's the usual kind of thought experiment people do when they talk about this. They talk about, oh my gosh, compound interest. And I don't remember if I did this in this class or the other class, so stop me if I, well, no, we'll do it anyway, because it's worth, because I didn't really do it that well in the other class. So you've got your compound interest formula. where you have the amount of money at time t is equal to your principal times 1 plus your interest rate divided by the number of times you're compounding it to the nt power, where t is in years. So let's pretend that I lent you $1 and I charged you 100% interest because I want to get paid. So we're starting with the principal being $1, the interest rate being 100%. We want to write it as a decimal, so that's just going to be 1. And the number of years, I'm just going to lend you this money for 1 year. So very, very basically, if I only compound the interest once per year annually, at the end of 1 year, you're going to owe me the $1 I lent you plus 100% of interest. So another $1. So after 1 year, you're going to owe me $2. And if I write the formula here, which I should do, my formula is going to become 1 times 1 plus 1 over n to the n power. Oh, that looks familiar. So after 1 year, in fact, you can see if I plug in n equal to 1, I get 1 plus 1, which is 2, to the first power, which is 2. But then if I start compounding it more frequently, I'm going to earn more interest. Is there a question there? Okay, sorry, you look like you're about like you're like waiting to raise your hand. So if we compound it twice, well, 1 plus 1/2 squared is really 3 over 2 squared, which is 9 over 4, which is $2.25. I earned an extra quarter by compounding the interest more frequently. Also, just to make sure everyone's clear with how this works, what's happening with compound interest is that if I'm compounding it twice per year, then after half of the year is over, I'm going to compound the interest. So I lent you $1, and then 6 months later, I'm going to get half of the 100% of interest. 50% of $1 is 50 cents. So now there's $1.50 that's owed to me. But now I'm charging interest on that amount. So now I'm going to charge you 50% interest on the $1.50 that you owe me, which is 75 cents. So after another 6 months, I'm going to get 75 cents of interest for $2.25. So that's kind of the very basic math of what's going on here. If you compound it more frequently, doing this gets to be kind of a pain in the butt, like actually showing all the work here. That's the idea. So now look what happens. If I compound interest quarterly, I'm going to end up getting 1 plus 1 over 4 to the 4th power, which is approximately $2.44. And if I compound it, say, monthly, I'm going to get, how much do I get here? About $2.61. If I compound it daily, 365 times, you get 1 plus 1 over 365, which is very, very not that big, right? 1 over 365 is, you know, 0.003, I think. That sounds about right. But if you raise that to the 365 power, you're taking that number that's pretty close to 1, but multiplying by itself so many times, you kind of overcome being so close to 1, and you get far away from 1. You get to be approximately 2.714, $2.71 and 4/10 of a cent. And as you might see what's happening here, we're getting closer and closer and closer to the value of E. So as you compound this interest more and more frequently, this value gets closer and closer to E dollars, $2.71 and some fraction. Yeah. Of a value of what? So like if I change the principal to like $5, so yes, so that you still have this multiplication factor. So for example, if I had said like he was 5, I would end up getting 5 times E here. Right. But I think your question might actually be more interesting if we change the value of R. So I will point out that this limit certainly, as n goes to infinity, of 1 plus 1 over n to the n is equal to E. And this question is really better to address once we've learned L'Hopital's rule, because then we can actually like do the whole thing and actually show the work as opposed to kind of just saying hand wavy things. But I'll point out that if your interest rate was different, like if I was really kind of feeling like I wanted to earn some money and I charged you 200% interest, right? So if R is 200%, or just 2. Then I've got this. I've got the amount of money I'm going to get is going to be still the $1 I lent you times 1 plus 2 over n to the nth power. How's that going to be different? Let's take a look. And why I'm not, so let's do away with the pretending of I'm just doing this with different numbers. Let me just show you. So if we look here we've got our 1 plus 2 over n to the nth power. And here we can see the values. If I compound it once, I'm going to get $2. Oh, I didn't, sorry, these are any new values here because I just changed that. Apologies. Oh my gosh, go away. Let me grab a new table here. Cool. So if I compound it once, I'm going to get $3 now, right? Because I got my dollar back plus the 200% interest that I was charging you. So no joke. And then if I compound it twice, $4. Compound it 4 times quarterly. That doesn't seem right. Oh, wait, there's a decimal there, right? That's 5.0625. Okay. If I do it 12 times monthly, $6.35. Daily, every minute. What number is that? I think it's e squared. So we're getting closer and closer to e to the second power, which makes a lot of sense if we do some clever manipulation here. So the idea here is that you can, if you think about taking the limit as this goes to infinity, well, you can rewrite this as 1 plus 2 over n to the n over 2 squared. Now this inside part is going to be getting closer and closer to just e, because you have the exact right thing. You have 1 plus a thing that's getting closer and closer to 0, and the exact reciprocal of that thing that's getting infinitely large. So the general idea here is that these two things have to match up to get closer and closer to e. So when you have the limit as n goes to infinity of 1 plus 1 over n to the nth power equaling e, really that n can be anything as long as it's getting infinitely large. So what I'm really just doing here is saying I'm replacing n with, say, n over 2. But I still have 1 plus 1 over something getting big raised to the something getting big, and those somethings are the same. So this still meets the criteria of doing the usual thing. And that limit's going to be e, which means if you then square it, you're going to get e squared. Two things here. The general idea, which I think this is a problem in the textbook somewhere, is that the limit as n goes to infinity of 1 plus x over n to the nth power is equal to e to the x. In the same way that this limit was equal to e squared. Just replace the 2 here with x, and you'll end up getting e to the x. The other thing I want to say is I kind of view this very, very similarly to kind of how like the limit as x goes to 0 of sine x over x is equal to 1. Right? It doesn't have to be sine x over x. It can be sine of anything over the same something. Right? So we know that you have the limit as like x goes to 0 of sine of 9x over 9x. That limit's going to be 1 because the something are the same. And so you're going to get, and then the sine of something over the same something that's going to 0, so the limit ends up being 1. Same idea over here. If I have the limit as n goes to infinity of 1 plus 1 over n over 9 to the n over 9 power, or as someone would more normally write this, limit as n goes to infinity of 1 plus 9 over n to the n over 9 power, that's going to be e because those are matching up. On the other hand, the limit as x goes to 0 of sine of 3x over 2x is going to be 3 over 2. We've seen this a few times, but we could use what I like to call the wish method and say, oh yeah, it's going to be sine of 3x over 3x times 3x over 2x. kind of weirdly there. Usually I write more fractions first and then like fill them in. I would have had sine of 3x over 2x and then filled in with the 3x over 3x there. And then we know that the limit of this part here is going to be 1. So we get 1 times that part's just going to be 3 over 2. The same kind of idea works over here. If you have the limit as n goes to infinity, let's say 1 plus 3 over n to the n over 2, you can do the same kind of thing. You really, really want this power up here to be the reciprocal of that thing right there. So here's what we're going to do. We're going to make it happen. I want this to be the limit as n goes to infinity of 1 plus 3 over n to the, I really want this to be n over 3. But then what do I need to multiply n over 3 by so that it ends up still equaling n over 2? Yeah, it's going to be 3 over 2. Because the 3's cancel, you're left with n over 2. But then if you're multiplying powers, you can really write that as a power to a power. And then you've got e to the 3/2 power. It's kind of weird, but it totally works. So that's how you deal with weird e things. Now, again, once we start talking about L'Hopital's rule, there's a whole other way to see this, which takes more kind of time. Like this is definitely the best. It's good to know the other stuff, but this is kind of the better way to deal with these so that you don't have to like spend so much time doing it. So there's some e stuff for you. So let me, yeah. Sure, yes. So let me ask you, for this one, why did 2 become the exponent? For this, actually, you know what? I didn't really finish it, so that's a fair question. So let me show you. So, but it's really the same idea. I'm trying to make, sorry, let me write things down here. I'm trying to make it so I have exactly 1 plus something raised to the reciprocal power, which I don't have currently. So I'm going to rewrite it. I'm going to rewrite it as the limit as n goes to infinity of 1 plus my something that's going to 0, right? X over n is going to 0. That's important. I want the power up here to be n over x. But if I have n over x, then I have to multiply by x, so I didn't really change anything. And then, oh, look, I think you all see what's going to happen. It's going to be the limit as n goes to infinity of 1 plus x over n to the n over x to the x. And then this inside part here meets the criteria. You've got 1 plus a thing that's going to 0 raised to a power that's going to infinity. So you have a 1 to the infinity that's going to equal, and the things match, right? X over n and n over x are reciprocals of each other perfectly. So this whole inside part gets to go to e. And then we have e raised to the x power. That's how that happens. Okay. Let's spend a little bit of time talking more about derivatives of logs and inverses. Yeah. Specifically, it's really just inverse tangent, right? There aren't any other inverse functions like, well, I mean, I guess the logarithm itself is an inverse function. But yeah. So let's remind ourselves of these new kind of derivative rules that we are supposed to have learned. So here they all are. So first and foremost, not foremost. First, the derivative of the, do you guys, is he writing it as arctangent or inverse tangent, or is he switching back and forth? I like arctangent personally. Derivative of the arctangent of x is 1 over 1 plus x squared. Or x squared plus 1, whichever way you want to write the denominator. They're both fine. Or you can write it as the derivative of the inverse tangent of x is equal to 1 over 1 plus x squared. When I write a derivative rule, you should all think to yourself, okay, what's the chain rule version? So I know the derivative of the arctangent of x is 1 over 1 plus x squared. So that would mean that then the derivative of the arctangent of some stuff, I'm going to write the letter u for my stuff. Well, I said the word stuff, so it should be 1 over 1 plus my stuff squared. And then I have to multiply by the derivative of the stuff, u prime or du dx, whichever way you want to write it. That's always the case, right? I've said it so many times, right? Whenever you're writing a chain rule version, you're just replacing every x with your stuff, and then at the end of the process, multiplying by the derivative of the stuff. Everything. There's a few other rules that we've learned in this section that we should talk about. So we have the derivative, and I'm just going to write these. So I'm going to write down like 8 rules here, but they're really only 2 rules. It's just that they're kind of larger and larger versions of the same rule. So we have that the derivative of e to the x is e to the x. And the derivative of the natural log of x is 1 over x. And then we have the chain rule version. The derivative of, e to the stuff is e to the stuff times the derivative of the stuff. And the derivative of the natural log of some stuff is 1 over the stuff times the derivative of the stuff. And then we have the versions with different bases. So I think we talked about a little bit, I think. We'll say it and then we'll maybe do an example. The derivative of b to the x, where b is a base that's positive, is equal to b to the x times the natural log of b. And the derivative of log base b of x is equal to 1 over x times the natural log of b. So here's what I always say to myself when I have a different base. For exponential functions, you end up multiplying by the natural log of the base. For logarithmic functions, you end up dividing by the natural log of the base. And then we have the chain rule version of these. The derivative of some other base to the stuff is going to be that base to the stuff times the natural log of that base times the derivative of the stuff. And then the same sort of rule for logarithms. The derivative of the log base b of some stuff is going to be 1 over your stuff. Natural log of your base is also down there. And then we have to multiply by the derivative of the stuff. Oh, over here. Terrible. Come back. Right. So there are ways of deriving these formulas, especially with the different bases, but I don't think you really need to. Let me point out what I mean. So if I wanted to find, say, the derivative of 7 to the x power, you could go about this a lot of different ways. There's probably at least 2 good ways to do this. One way to do this, if you didn't just memorize the formula, would be to rewrite it as the derivative of e to the natural log of 7 to the x power. And then that's going to be the derivative of e to the x times natural log of 7, or in other words, the derivative of e to the stuff. But we know the derivative of e to the stuff. The derivative of e to the stuff is going to be e to the stuff multiplied by the derivative of the stuff. What's the derivative of x times natural log of 7? Say it one more time. Exactly, right? It's just the derivative of x times a constant, and the derivative of x times a constant is just the constant. So here we get just the natural log of 7. Now I want to point out this is not how we like to leave our answer, because we know that e to the x times natural log of 7 is the same as e to the natural log of 7 to the x, which is the same as 7 to the x. So really we should write this as 7 to the x times natural log of 7. Not surprising, right? We knew that the formula was going to give us our original exponential function times the natural log of the base. It also works even for bases e, right? The derivative of e to the x is e to the x times the natural log of e if you want it there. You don't need to write it though. The other way of doing this, which I think is interesting, is I want to take, say, the derivative of 5 to the x. I know what the answer is going to be. It's going to be 5 to the x times natural log of 5. But if we choose to, we can do this implicitly. You can say we're going to start with y equal to 5 to the x. Take the natural log of both sides. So the natural log of y is equal to the natural log of 5 to the x. But then the natural log of 5 to the x is x times the natural log of 5. And if we take the derivative of both sides here, implicitly, the derivative of the natural log of y is going to be 1 over y times the derivative of y. On the other side, the derivative of, well, just like before, the derivative of x times the constant is just the constant, just the natural log of 5. And then we can multiply both sides by y, so that y prime is equal to y times the natural log of 5. And then we can get that y prime is equal to y, which was 5 to the x times natural log of 5. So either way you want to get there is fine, but really at the end of the day, you don't want to do either of these. You want to memorize the fact that when you take the derivative of b to the x, you get b to the x times the natural log of b. And we take the derivative of b to the stuff, you get b to the stuff times the natural log of the stuff. Sorry, times the natural log of b times the derivative of stuff. So with that in mind, let's find some derivatives. Let's try finding the derivative of 3 to the arctangent of x. So I'm thinking I've got 3 to the stuff. All right. Derivative of 3 to the stuff is 3 to the stuff times. There's not like a good, there's no like set way of saying this. You can either say the natural log of the base first or the derivative of the stuff first. I don't really have a preferred way. So I'm just saying I've got the derivative of 3 to the stuff, and it's going to be 3 to the stuff times the derivative of the stuff, which is 1 over 1 plus x squared times the natural log of the base. You could simplify this by writing it all in the numerator, but I don't think you need to. Like you could write it as 3 to the arctangent of x times the natural log of 3 all over 1 plus x squared, but I don't find that to be particularly helpful. But there, look pretty. Why don't you try finding this following one? Derivative of the arctangent of log base 2 of x plus x squared plus 3. Oh, it's terrible. I don't like that at all. Chain rule and a chain rule. Let's do it together. So working from the outside in, we have the arctangent of some stuff. The derivative of the arctangent of x is 1 over 1 plus x squared. So the derivative of the arctangent of some stuff is going to be 1 over 1 plus all that stuff, log base 2 of x squared plus 3 squared, times the derivative of the inside here. So now I'm focused in on this. Saying, great. I have to take the derivative of log base 2 of some new stuff. I know the derivative, the natural log of some stuff is 1 of the stuff times the derivative of stuff. The only difference here is that the base 2 means somewhere in the mix, I also have to divide by the natural log of 2. So I'm going to get 1 over the stuff, the x squared plus 3. I also want the natural log of my base down there. And then I need to multiply by 2x, the derivative of the stuff. So again, when I'm dealing with logarithms of a different base, I know that the natural log of that base has to end up in the denominator. When I'm dealing with exponential functions of a different base, I know I need the natural log of that base in the numerator, or just multiply by the natural log of that base. Let's see, what else is on my mind here? Okay. So one more thing here, and then we can start going that way. Yeah. Oh yeah, no, we should go that way. Let's talk about linearization, because we haven't talked about that really. I think we did like one brief example at the end of class last Thursday. So linearization, and I think that's what he finished class with on Friday, was linearization. Did he talk about Taylor polynomials at all? I mean, he did, but like, did he say those words? No. Okay. We'll yeah, let me actually take a quick look and see what he's assigned. Yeah, he assigned some of those Taylor polynomial problems. We should definitely talk about them. Yeah, okay, cool. So I know I said it last week, but I'm saying it again, linearization, you're just finding the equation of the tangent line. So to linearize a function f of x at a particular point, usually labeled as a comma f of a, we're just finding the equation of the line tangent to y equal to f of x at that point. And just like any line equation, you need two things. You need a point and you need a slope. Our point is just going to be the point a comma f of a. Our slope, we are going to use the derivative, and the slope is going to be the derivative at the point of tangency, which is going to be f prime of a. So putting these two things together in a general way, we can say, great, our equation is going to look like y minus the y coordinate equal to your slope times x minus the x coordinate. But we never write it this way, which is too bad, because I feel like it'd be great if we wrote it this way. It seems nicer. We solve for y, and then we typically replace y with the capital L of x. So we're gonna just call y a new name, and we're gonna say, great, our linearization L of x is equal to f of a plus f prime of a times x minus a. We typically do not simplify it, meaning you don't actually take whatever your slope is and multiply it by x minus whatever your x coordinate is, and then add on whatever your y value is. You leave it like this, because then it allows us to easily use it to estimate things. So typical questions that revolve around linearizations are things like, sorry, you can't see that. Apologies, I meant to leave it on the board there. We can say something like, use a linearization to estimate. Let me think for a second before I get too wild here. 2.03 to the, let's say to the 5th power. Yeah, question. Probably, yeah. F prime of a right there. Yeah, it's F prime of a. But again, when you read this, what you should really be thinking when you're writing this down, why do I not have any red pens in here? That's like terrible. So I guess what you should be thinking here is that, right, this is just your y value. This is just your slope. This is just your x value. Yeah, you can really read that, I'm sure. Right? Sorry. Let me write it the tiniest way I can. There you go. What's that? Oh no, I'm good. It's fine. It's not that bad. Well, that's nice. Okay, so 2.03 to the 5th power. I know you can't see right now, but 2.03 to the 5th would be terrible to actually calculate by hand, right? To do like 5 multiplication, like it's gonna get real gross. Yeah, I know we could use a calculator, but the whole point here is that people used to not have calculators, and they did these calculations, and they found clever ways of estimating things without needing powerful computational tools. So we're gonna do it like they used to do it. Use linearization to estimate this thing. Yeah, fine. So just to remind you all of the picture, what's happening here, right, is we've got some function 2.03 to the 5th, which looks or sorry, well, let me back it up actually. So before I get too carried away here, before you can really even do this, you have to identify the function you're going to need. And usually that function is just take whatever looks like the input is, in this case, the thing that's problematic, the 2.03, replace it with x. So I'm thinking, okay, great, I want to try and do that. So my function should be x to the fifth. And so now I'm going to see, okay, well, x to the fifth, again, we don't need this picture, but I just want you to make sure everyone's cool with the idea of what's going on is that we're going to, well, we're going to pick a convenient point, 2, right? It should usually be pretty obvious what the convenient point is. It's a value that's easy to plug into the function and calculate yourself without a calculator. So here our convenient value is 2. And then if we look at the tangent line here, the whole idea is that then to calculate what's happening at 2.03, instead of getting the actual function value up here, instead of getting that actual function value right there, we're going to get the linearization value, which is a little bit away from it. In this case, a slight underestimate. Sometimes it'll be over, sometimes it'll be under, depends on what your graph looks like. It really depends on the concavity of the graph, actually. If your graph is concave up like this one, it'll end up being an underestimate. If your graph is concave down, it'll end up being an overestimate. And we haven't talked about concavity yet. That's chapter 4. We're almost there. So we're expecting an underestimate. Great. And now the rest of this is really just taking the formula and I mean, you could do it the long way and think about finding the equation of the tangent line, but you could just do it the short way and say, great, I know the formula. Formula is going to be my linearization. The equation of my tangent line is going to be f of a plus f prime of a times x minus a. And I suppose it's probably worthwhile to write down what a is. We all said it, well, some of us said the convenient value of choice here is 2. That's what your a value is. A is your convenient number to plug in. F of a in this case is going to be 2 to the fifth, which is 32. And f prime of a, well, the derivative here is 5x to the fourth. So f prime of a should be 5 times 2 to the fourth, which is 5 times 16, which is 80. So the equation of our tangent line or linearization here is going to be 32 plus 80 times x minus 2. Now I want to point out, simplifying this is a bad idea. If I'm trying to use this to estimate what happens when x is equal to 2.03, it's not helpful for me to multiply this out and get 80x plus 32 minus 160 and then make that whatever. I don't want to find 80 times 2.03. I want to find 80 times 0.03 because that's just easier. It's not that much. Okay, this one maybe I'm exaggerating a little bit how much more difficult it is, but in general, it is usually almost always better to not mess with this at all. So leave this as is. There's our linearization. There's our linearization at the point 2, 32. And then we're going to use that linearization to estimate 2.03 to the fifth. So I'll point out that 2.03 to the fifth is just our function f evaluated at 2.03. And the whole idea here is we're going to say, great, we're not actually going to find that. I don't care what 2.03 to the fifth actually is. It's approximately equal to my linearization evaluated at 2.03, which is just going to be 32 plus 80 times 2.03 minus 2. That's going to be 32 plus, let's see, 0.03 times 80. 3 times 8 is 24, so that's going to be a 2.4. Yeah. Yeah, 2.4, right? 2.4. It shouldn't be two. So it should, just thinking about it logically, right? If it was 24, 32 plus 24 is far away from 32. 2.03 to the fifth should probably be pretty close to 32. So yeah, 2.4 here seems reasonable. So we're getting 34.4. And now it's always fun, I think, to check what the actual value is to see how close we were. So if you look at 2.03 to the fifth, actually, 34.47. I mean, approximately, right? There's more decimals that I don't want to write. So yeah, our estimate's pretty close. Linearization at, yes. At the point 2 comma 32. So typically, when someone says use the linearization to estimate this thing, this is what they expect you to do. They expect you to find the linearization and then use that linearization to estimate the value near whatever the actual nice value is. So typically, it's your job to find the function, find the convenient point, and then also find the derivative at that point to find the equation. Those are the three things you usually have to find. We should probably do another example. Okay, so, sure. Oh, there's also that stuff too. Yeah. Has he talked about Newton's method too? No, but he's assigned some problems from Newton. He's assigned one problem from Newton's methods. We'll talk about that, I guess. Sure. So let's see. Let's not be too basic here. All right. Yeah, let's do that one. So let's use a linearization to approximate e to the 0.1. Nope, you can't see that. Sorry. So I want you all to do the following three things. Figure out what your function needs to be. Might as well find its derivative as well. And then figure out what your a value needs to be. The value that's close to what you have to plug in that's easy to evaluate. By the way, there's only one value that's easy to plug into e to the x. And then find your f of a and your f prime of a. Do all that. Think about what the function should be. Instead of e to the 0.1, you want it to be e to the. And then write down the linearization. Don't go away. Sorry. Can I move this out of the way? Maybe not. Maybe we're stuck with this forever. This one's kind of boring almost. Our function's e to the x, derivative is e to the x. Our easy value that's easy to plug in, or a value of the function that's close to what we're trying to plug in is 0. And that's really the only thing you ever have. Or I should say, whatever makes your exponent 0. So like if the function was e to the x plus 3, then the point we'd probably be looking at is plugging in -3. Although usually you try to make the function as kind of simple as possible. Our derivative at 0 is 1. Our function at 0 is 1. So then our linearization is going to be, I do think it's worthwhile to write down the formula every time. So I always like to write down f of a plus f prime of a times x minus a. But here we're just going to get 1 plus 1 times x minus 0. Or in other words, our linearization is just 1 plus x. Which shouldn't be surprising because if you look back at the graphs, the graph of e to the x is that blue one. The graph of y equals x plus 1 is that purple one. And it's exactly the graph of the line tangent to the function at the point of linearization. Every time. That's what we're just finding a tangent line. We've just kind of for some reason that's unfortunate, we've removed it from its meaning, kind of, which is too bad almost. So then to do the approximation, we're going to say, okay, e to the 0.1 is approximately the linearization at 0.1, which should be just 1 plus 0.1, which is 1.1. And then we might as well compare, because Why wouldn't we compare? 1.105, so pretty close. They're usually pretty close. Actually, as long as the place that you're plugging in is relatively close to the point of tangency, your estimate should be pretty close. If you move far away, like if we tried to use this to estimate e to the second, we'd be way off, right? E to the second, if you plug in 2 for this, you get 1 plus 2, which is 3. We saw that e to the second was like 7.4 approximately way back when. So definitely only good for values close, not ones far away. I feel like the better thing to talk about next is the other Taylor polynomial stuff because there's a nice pattern there. So there's two other estimate things we like to do. One of them is Taylor polynomials, which really, so I will point out what we just did is a Taylor polynomial. We'll talk more about that in a second. There's also this other method of estimating things called Newton's method, which is super annoying in my opinion. It's kind of like, it's actually very much like a recursive sequence where you use the whole method to find the value, and then you take your new value, you kind of plug it back into the whole thing to find another new value. You kind of keep doing that until someone tells you to stop, or until you've gotten close enough to the answer. Well, let's talk about the rest of the Taylor polynomial stuff because I think it's kind of easier to see what's happening. So I will point out that the linearization, which is f of a plus f prime of a times x minus a, good God, James, is the first degree Taylor polynomial. And a Taylor polynomial is, I know I'm saying these words I haven't like said what it is. A Taylor polynomial is a polynomial. It can be up to whatever degree you want it to be, that gives you a good estimate of an actual function. And the more degree you have, the closer the estimate gets. Now, there's kind of really nice way of, there's a whole there's a whole study of Taylor polynomials you could do. But there's a very kind of nice, easy way of remembering how the formula works. So we'll talk about the formula for a second, then I'll give you an example. So here's the first degree Taylor polynomial in general. Second degree, here's what you're going to do. You're just going to take your first degree stuff, f of a plus f prime of a times x minus a, and you're going to add on one more term. And the next term is always going to be found in the same way. It's going to be the next derivative, so f double prime of a, times the next power of x minus a. And then you have to divide by the next number factorial. 2 factorial in this case. Everyone, so just as a, so everyone, like factorial just means you take that number and multiply by all the lesser numbers down to 1. So like 7 factorial is 7 times 6 times 5 times 4 times 3 times 2 times 1. 2 factorial is 2 times 1. We didn't write, whoops. Sorry. We didn't write it over here, but technically we are dividing this by 1 factorial, but 1 factorial is equal to 1, so we don't write it. And also technically we are dividing this by 0 factorial, and yes, annoyingly, 0 factorial is also equal to 1. Actually, not annoyingly, very usefully. It would be really terrible if 0 factorial was equal to 0 because we have some problems. I won't say too much about that. I'll just say that 0 factorial is equal to 1, kind of like 6 to the 0th power is equal to 1. And it's kind of a rule that, because of other rules that have to be true, like the additive law of exponents, 2 to the 0 has to equal 1. In the same sort of way, because of other rules and formulas that need to be true, we end up having to have the 0 factorial is equal to 1. So then if you wanted the third degree Taylor polynomial, I bet you all can write it down. It's going to be all of this that we just had. And I bet you all could make a pretty good right-on guess about what the next term is going to be. I'll give you 30 seconds to do that. When you say the amount of time, you should actually keep track of the time. So as you probably guessed, the last term of the third degree Taylor polynomial is the third derivative evaluated at a times x minus a to the third divided by 3 factorial. And I feel like at this point you can guess the rest of them, right? The fourth degree Taylor polynomial is going to be all these terms plus the next thing, the fourth derivative times x minus a to the fourth divided by 4 factorial, and so on and so on and so on. So then the idea is we can use these Taylor polynomials to get better estimates of a function at a particular point. So for example, if I went back to my, say, my estimating 2.03 to the fifth power example, if instead of using the linearization, I said using the second degree Taylor polynomial, okay, well, that's a little bit more interesting. So let's go ahead and write it out. I know that my f of x was x to the fifth. I'm going to need a second derivative now here. So my f prime of x was 5x to the fourth. My second derivative was 20x cubed. And then I know that f of 2 is going to be 32 still. F prime of 2 was 80. And f double prime of 2 is going to be 20 times 8, which is 160. So then I know that my secondary Taylor polynomial, which we write as p sub 2 of x, I'm just going to plug all that in here. So it's going to be my f of a, which is 32, plus my f prime of a, which is 80 times x minus a, so x minus 2, plus my f double prime of a, which is 160, divided by 2 factorial, which is just 2, times x minus 2 squared. The thing about this is things start to get, so at this point, things are going to be kind of dicey numerically because we're going to have a decimal squared. So using the Taylor polynomial often isn't better than just pulling out it. Well, it's not easier to do than trying just to do the math itself in the first place. Yeah. Because my formula says the second derivative divided by 2 factorial. And 2 factorial is equal to 2 times 1. Just like 3 factorial is equal to 3 times 2 times 1. So then plugging in 2.03, I get that 32 plus 80 times 0.03 plus 160 over 2 is 80 times 0.03 squared. And if we plug this all in, I'm going to get 32 plus 2.4. And then this part here, the reason why we almost always just use a linearization is because this part here is going to be pretty negligible, right? If I do 80 times 0.03 squared, it's going to be 0.072. So my answer here is going to be 34.472 compared to my 34.4 of last time. So all that work didn't really get me a whole lot closer to the answer that we had before. And the actual value, again, was 34.47. So yeah, we did get closer. You guys, can you see that? I can't see that. Can you see that? So it is 34.47 approximately. So our answer is closer, but was it worth the price of the work we did? I don't know, probably not. But that's kind of the idea, is that you can use, so really, yeah, point really here with these Taylor polynomials isn't so much that we can use them to estimate points of things, but you can actually use them to estimate a function. So just let me show you one more example in the last 2 minutes, just because I think it's kind of cool. So let me show you this one. Where'd you go? This way. I don't love you. Let's not do that one. Let's do the following one. So you can use Taylor polynomials to kind of approximate almost any function. Here's a very common one. So here's the beginning of the Taylor polynomial. Here's the first degree Taylor polynomial. Not very exciting, but it certainly does estimate the function very well near the origin, and also the derivative very well. But then if we add on more terms, oh look, it's better for longer, right? Now kind of between like -1 and 1, it looks pretty good. If I add on another term, even better. And you can kind of keep doing this literally forever and getting a better and better approximation of your function. So the Taylor polynomial for sine of x is every odd power of x divided by the corresponding factorial, and the sign alternate. So the next term would be plus x to the 9th over 9 factorial, then minus x to the 11th over 11 factorial, and so on and so on and so on. And if you write the infinite Taylor polynomial, it actually is the sine function. And what's useful about this is then sometimes there are crazy functions that don't really have nice derivatives or antiderivatives, but you can use their Taylor polynomial as an approximation of them and do the derivative or antiderivative of that. And that's much easier to take the derivative of a polynomial or the antiderivative of a polynomial. So that's one thing Taylor polynomials are really useful for, is as stand-ins for functions that are kind of terrible to deal with in other situations. All right, that's all I got to say.